Okay, well, it's a great pleasure to talk to you today. Um, I'm sorry I cannot be there in person. It's not much related to the pandemic, but more to my kid and being uh, here for her and taking her to school. And in fact, you got me out of taking her to school this morning, so thank you very much for that. Um, so I'd like to talk about a project that we've been working on in my group and with other groups in the States for a few years now. Um, and so this is a project that was started by one of my graduate students, Zhaojian Bai, who is now faculty in Louisiana in the southeastern United States. And he got the idea to look at this material, FeI2. And then we did a lot of neutron scattering experiments in my group, and then worked a lot with the theory group of Christian Batista. And as things progressed with the project, we also worked with a group of Peter Armitage, who is doing terahertz spectroscopy, optical spectroscopy. So this project really combines different types of spectroscopy and theory to understand the nature of excitations in one of these quantum magnets. I should say that all the experiments neutron-wise were done at Oak Ridge National Lab, which is close to where I am, Georgia Tech, a 3-hour drive. And some of the crystal growth was done in a national facility we have in the US, where you can propose, if you have a crystal that is of interest to you, you can propose it as like you would do a beamline proposal, and they can help you. Tara McQueen's group can help you grow that crystal using outstanding facilities they have there at Johns Hopkins. So let me get started with talking a little bit about one of the background for this project, which is to look at multipolar states of matter in magnetic systems, multipolar order or multipolar excitations. So one way we can classify phases of magnetic matter is to consider a local order parameter. And we all know that at the lowest order, we're going to have dipole moments, and usually in a magnet, there is a spin order, so it means these dipole moments organize in a certain way that breaks several symmetries, including spin rotation, translation symmetry, and other things. It's also well known, and we have a lot of experts that participate in that workshop, that we can also construct local order parameters that have a high order, so that could be quadrupolar or octupolar order parameters. And if you have a phase of matter which degrees of freedom have this character, you can create perhaps novel states which break only certain symmetries, and maybe we can call them in general spin nematic systems. They still have a local order parameter, but that local order parameter is of high order. And perhaps far along this, when you consider very exotic systems, you need to construct orders that do not have a local nature. And this is what happens in quantum spin liquids, where the order that is broken is a topological in nature, and there is no apparent symmetry breaking in the system. And so these are very exotic phases of matter that a lot of people are looking for. And perhaps this quadrupolar or octupolar phases, or the excitations, are a stepping stone towards topological order, although they have local characteristics. And so I will talk in this FeI2, as we will see, is a system that has quadrupolar excitations. And this is what we studied in detail. So in general, it's a frontier in our field to stabilize these multipolar spin states. And so that means a state that has zero expectation value for dipoles and perhaps non-zero expectation value for quadrupolar or several quadrupolar order parameters. And so the question is where you can find such states. And one thing you can immediately think about is that, okay, I will create quadrupoles in my system by working with anisotropic magnetization distributions. So you can do this in, for instance, rare earths or lanthanides or actinides, where you have a crystal field environment that naturally lends itself to creating a crystal field multipole that may have the characteristics that I described above. For instance, zero expectation value for dipole operators and non-zero for quadrupolar operator. So there's a lot of materials. I'm not citing them all here, but it's a well-known approach to search and potentially stabilize these quadrupolar phases. Obviously, here I'm talking about systems that would have local magnetic moments. You can also imagine creating multipolar states in metals, or systems that are that have a Fermi surface. I'm not an expert on that, but you could imagine that doing that with electronic nematicity in various systems. And if you do not have local multipolar degrees of freedom available to you, you could imagine taking dipoles and coupling them, for instance, with ferromagnetic interactions to create new degrees of freedom that live on the bond of a lattice, and that would have that more complex nature than dipolar. So that's a very cute example of doing this in J1, J2 chains, where J1 is ferromagnetic and J2 is antiferromagnetic, and there is a lot of phases and a lot of exciting physics you can access in this model Hamiltonian. And on top of that, there's a few cool materials that do that. And finally, I mean, that list is not exhaustive, but you could imagine working with systems that have a larger Hilbert space than spin 1/2. So for instance, spin 1 systems, and in presence of biquadratic exchange, you can stabilize these quadrupolar phases. So many people have worked on that, and you know, this is not my initial background in magnetism, and so everything I learned from talking to Mike Zitomieszky initially, and from the outstanding thesis of Tamás Stott at EPFL in 2011. Anyway, in general, for experimentalists, the challenge is to observe these multipolar degrees of freedom, be it the ordered part or the fluctuations of these multipolar degrees of freedom. And I'm a neutron scatterer, so with neutrons, usually we do not see these degrees of freedom. And that's because these excitations carry a change of spin angular momentum of 2, and usually these excitations are not seen by neutrons. However, they might be seen by other techniques such as Raman or inelastic, resonant inelastic X-ray scatter. But if you're interested in the fluctuations and not in the order, there's a trick you can play, and which is to hybridize your quadrupolar fluctuations with something that you see. And one example that happens in uranium oxide is that these quadrupolar fluctuations that come from the crystal field of the uranium, they actually couple to phonons. And because with neutrons you see the phonons, you can see the hybridization, and in some sense you see these hidden fluctuations that are quadrupolar nature. And what I will show today, essentially the upshot, is that in FeI2, a similar mechanism occurs, so to speak, where the quadrupolar fluctuations and higher order fluctuations even are coupled to magnons, and because we see the magnons, we can understand the system. So a brief discussion of neutron scattering. I know that Belalay gave a nice introduction to that technique, so I will be brief. I'll just remind you that neutron scattering is an outstanding technique to study magnetism for various reasons, but one of them that is really useful in this talk is that what we are measuring in our detectors, the double differential cross-section, which depends on the momentum, energy, and spin that we transfer to the sample. Well, that double differential cross-section is directly related to a quantity called the dynamic structure factor. And the dynamic structure factor is the Fourier transform in space and time of 2-point correlation functions. Okay, so as a result of this, we can study what happens in our system as a function of time and space. Of course, it's a Fourier transform, and so the devil is in understanding that Fourier transform, but it's a direct access to what the spins do and how they move, so to speak. And there's a related quantity we call the instantaneous structure factor, which is the energy integrated dynamics, and that gives you instantaneous pair correlations. So that's, so to speak, a 4-dimensional data set. That's a 3-dimensional data set. So we like to use that 3-dimensional data set sometimes because it's easier to analyze. So I will show this in this talk a little bit. I just want to briefly explain one aspect, which is that the instrumentation in neutron scattering has evolved rapidly. And this is the latest generation of instrumentation that has allowed us to do which we've done in this project. So traditionally, studying excitations with neutrons relies on the triple axis machine, where you essentially mapping Q and omega space point by point. So if your signal is localized in momentum energy space, that's actually a great technique, and you can apply large magnetic fields and pressure. It's very convenient in that sense. But this is not very efficient. And recently, or at least in the last 20 years, and in the States, really in the last 10 years, another type of technique called time of flight, where instead of using one detector, we use many pixels that detect the signal. These machines have allowed us to map huge volumes of momentum energy space. Essentially, it's a parallelized detection system. And that really has allowed us to see things we didn't know to look for before. So in brief, these time of flight machines are awesome to study quantum magnets, and I will show you some of the data about this today. Just a quick advertisement for the fact that in the US we are interested in building a new neutron source at Oak Ridge that will rely on the previous on the current accelerator, sorry. And so this is called the Second Target Station. And so this is a project that is going along with the Department of Energy. And so this new neutron source will have one key advantage is the flux of cold neutrons. So although neutrons are awesome, they're also difficult to produce, and we don't have enough of them. And that new neutron source, because of many advances in technology, would have a dramatically increased flux of cold neutrons, which is exactly what we need for quantum magnetism and correlated electron research. So we're very excited about this. And I'm involved in one project, an instrumentation project there. Anyway, so let's dive into the physics of this material. And so I will start with the toy model and to understand how it works, and then we'll add some ingredients. So viewed from above, FeI2 is a very simple material. It has spin 1 from the iron. It has ferromagnetic interaction and an easy axis anisotropy. So it's a full 3D material, but I will isolate a chain of that material just for the sake of argument. I'm not saying that it's a 1D system. I'm just isolating a particular part of the system. So there's two things we will do. Because we work with a spin 1 system, we will represent the local Hilbert space faithfully by taking into account that there's a +1, a 0, and the -1 state. And therefore, the operators that can act on that Hilbert space have both dipolar and quadrupolar nature. And then, in terms of how this local Hilbert spaces are coupled to each other, we will simply have an easy axis anisotropy that forces the spins to point up and a ferromagnetic interaction in the system. So this is a very trivial ground state. It has non-zero expectation value for the dipole. It has also non-zero expectation value for the quadrupole, Q is the Z operator, but of course, this is a secondary order parameter, so really this is a dipolar ordered system. And what's important to realize is that I will work in the limit where the anisotropy, so this D interaction, is 10 times greater than the exchange interaction, okay? And then we can ask ourselves, what do we expect to see in such a material, for instance, with neutron scattering? And so, of course, the simplest thing you can do is flip one spin from +1 to 0, and so you get this delta is equal 1 excitation. This is your 1 Magnon excitation. It costs you certain energy. And then if you consider, so to speak, the two-particle sector, you can imagine creating 2 single Magnon excitations on different sides. But because you have a ferromagnet, you can also imagine putting, or at least in that direction, you have ferromagnetic interactions. You can imagine putting the 2 Magnon excitation next to each other. And that lowers a little bit the energy because of the ferromagnetic interaction. So this 2 Magnon bond state is stabilized compared to the 2 Magnon free states. That's a well-known property of these ferromagnetic systems. But of course, these excitations are delta is equal 2, so we don't usually see them with neutron scattering. But because you have spin 1, you can also do something else, which is to take 2 single Magnon excitations and put them on the same side, so to speak, or flip the spin twice. You can do that because the Hilbert space allows you to do this. And now you create another type of bond state, which we call, or people call, the single ion bond state. It corresponds to flipping the spin twice, S minus, S minus. So this has a mapping to quadrupolar operators. And if the easy axis anisotropy is large, so D is large, this stabilization energy is actually the dominant stabilization. And this excitation can be the lowest energy state in the system. So if you work in SU3, so if you consider explicitly this local Hilbert space to have +1, 0, and -1, this comes naturally. If you work with pure dipoles, you can also create this bond state, this one, but that requires to some infinite amount of diagramming perturbation theory. So sorry, this one you can create with dipoles, but this one you cannot create if you only consider dipoles, because it's a local on-site excitation you do not have in say a spin 1/2 system. Okay, good. So just what we expect in a system like this is that we will not see the we will see the delta SD equal 1 excitations, but we will not see the delta SD equal 2 excitations. So these quadrupolar modes are there, but we don't see them. So let me show you that in FeI2 they actually show up. So this material has the right crystal field to stabilize. It's a transition metal system. It has the right crystal field to stabilize local Hilbert space with effectively spin 1 and a large single ion anisotropy. It's a triangular lattice, layered triangular lattice material. So it's actually a van der Waals system. You can exfoliate it if you want. And it has a complex set of exchanges in the plane and between the planes. But that stabilizes magnetic ordering at 9 Kelvin. And the magnetic structure has the propagation vector 1/4, 0, 1/4. So it means you create, so to speak, stripes with 2 spins down, 2 spins up, 2 spins down in the plane. And that kind of repeats over 4 unit cell along the C direction. So that complex magnetic structure requires at least the J3 in the plane and the J2A prime between the planes. So there's a lot of exchanges in the system that are active. But really, the reason we started looking at this is some very cool and neat far infrared spectroscopy from the 1980s, where people looked at the optical absorption of that system as a function of magnetic field. And what they found is that okay, there are several one Magnon branches. This is not too surprising given that you have a complex magnetic structure. But they also observed an absorption line that seems to split with twice the G factor of the one Magnon. And that's where they attributed this to the single ion bond state. And really the question is, why is this excitation visible? And what is the magnetic Hamiltonian that actually creates it? So we set up to study this material with neutron scattering. And to do so, we had to move from so this should be CVT here, sorry. We moved from CVT, chemical vapor transport crystals grown in my lab, to this very large 5-gram Bridgman grown single crystal we grew at the Paradigm facility. And with such large crystal, we can really do detailed neutron scattering measurements. And so that's the result. We use one of these time of flight machines. Here, this is the momentum transfer in the triangular plane. And here, this is the energy transfer to the sample. The system is in the ordered phase at low temperature. And you see essentially the 2 bands that the optics folks saw in the 1980s. The first band here, we call it the 1 Magnon. And by analogy with the optics, we call the second band the single ion bond state. And these excitations are really peculiar. In fact, we had never seen excitations looking like this before. In particular, you see that between these 2 bands, there seems to be a gap here. And in some parts, the single ion bond state is very flat. In some parts, it acquires a dispersion. And as you will see, we are seeing a hybridization phenomena. This is a simple, so to speak, hybridization phenomena between 2 bands of different quantum numbers. But you see, with this time of flight data, we have a lot of details available to us to understand how the system works. So the problem is that we don't have the Hamiltonian. And as I told you, it's quite complicated. So simply because the magnetic structure is not trivial, so there should be a lot of exchanges active in the system. And so we've developed ways to understand this progressively. And one trick we use is we actually warm up the system to its paramagnetic phase. So here, 11 Kelvin. And we are measuring S of Q, meaning we are measuring the momentum-dependent susceptibility, chi of Q, if you wish. So we're doing susceptibility measurement, but momentum resolved. And as the susceptibility allows you to get the Curie-Weiss or the Weiss constant of your material, momentum-dependent susceptibility allows you to get more details on the exchanges. So we have developed this technique where we look at the system in the paramagnetic phase, and we can fit the data to something called the self-consistent Gaussian approximation, and we can get the value of the exchanges in the system. You see here, J1 is ferromagnetic, and then we have significant J2, J3, out-of-plane exchanges, and a very large single ion anisotropy. So then what we do is we take these exchanges and we plug them in a linear spin wave calculation for dipoles. And what you see is that essentially the bandwidths and the oscillations of the excitations are well captured. However, this gap between the 1 Magnon and the single ion bond state is not there because the single ion bond state, the double spin flip excitation, is not is not in the theory. So, but this is good because it's telling us we're doing something meaningful. And then, of course, what we need to do is to treat these two local excitations on equal footing, and not only treat the dipole part, but also the part with double spin flip, which is the quadrupolar part. So again, the system is dipolar ordered. This is a conventionally ordered system. However, we want to treat its excitations, both dipolar and quadrupolar, single spin flip, double spin flip on the single side. We want to treat them on equal footing. And this is where we interacted with the group of Christian Battista. And essentially, we are doing a linear spin wave theory, not for in SU2, not for dipoles, but in SU3, where we have these two local excitations available to us. So that's a well-known approach that people have used time and time again. We do a Schwinger boson representation where the single spin flip and double spin flip should be a -1 here, sorry. This are represented by two different bosonic operators, and that gives us access to this complex Hilbert space. But we need another ingredient, and the other ingredient comes from something called anisotropic exchange. So the sample has low enough symmetry that the J1 exchange, the nearest neighbor exchange, we can write it as a matrix, and that matrix has 4 independent coefficients. And you can write it in different ways. The simplest way to think about it is that you have a diagonal term, which is the XXZ anisotropy, and then you have 2 off-diagonal terms, which we call JZ plus minus and J plus minus plus minus. So this couple the Z and the transverse terms, and that couples the transverse terms together. And so if you want to fit the data, so to speak, what you need is a term that has the structure JZ plus minus. So it means a SZ S plus term in your Hamiltonian, because when you write it in terms of Schwinger boson, you see that you are, for instance, destroying a single Magnon with state 0 and create a single ion bond state with a quantum number -1 here. So this term naturally transmutes a single Magnon into a single ion bond state. And that's what you need to fit the data. And these are the exchanges that we can fit from the data. And you see that this anisotropic exchange is large. It actually dominates the J1 interaction. And this is what is needed to explain the data. So what is really going on is that in presence of this off-diagonal exchange, JZ plus minus, the two bands of excitations, single Magnon in blue, single ion bond state in red, they overlap. And because of that interaction, they hybridize. And you see that the excitations are completely hybrid. They are neither dipole or quadrupolar. They are a mix of the two. And depending where you are in momentum space, and energy, your excitations have different character. So because every eigenstate comprises a little bit of single Magnon, we have a cross section to it. We can see it with neutrons, and that's how we see that beautiful data. So the message here is simply that we can see these quadrupolar fluctuations in a system with large spin-orbit coupling where anisotropic exchange is present because we can hybridize Magnons and quadrupole excitations. Good. So then we'll accelerate here a little bit. But this material, we were just here looking at the low temperature phase. This material has a lot of interesting phases at high field. That's actually initially why we were interested in looking at this thing. And when our first paper was published, I got a nice email from Louis-Pierre Rognot, who is a very distinguished neutron scatterer. And he emailed me that they actually solved the magnetic structure of this material back in the 1980s in all the possible phases. But unfortunately, he had to throw the data in the trash when he retired. And the student that worked on this never published the thesis. So essentially, the message was that, oh, we know everything, but I cannot tell you because it's in the trash. So at the moment, we are working on solving all the high field magnetic phases of the system. But what I want to show you today is what happens when we go a little bit with more fields and apply a field all the way to 4.5 Tesla. We stay in the same magnetic structure. And here we use terahertz spectroscopy, which is an outstanding technique to study excitations as a function of a lot of different magnetic fields. So this is the data. Imagine it's a Q0 map of what is going on. You see frequency here as a function of applied magnetic field. And so this is the right polarized, you're coming with polarized light in your sample. So this is the right polarized. We can also do the left, they can also do the left polarized. And what they send in the system is time domain terahertz pulse. When you Fourier transform, this time domain pulse is, so to speak, a broadband pulse. And so that's a very efficient way to actually measure the excitations in your system as a function of magnetic field. And you see they have a lot of magnetic fields they can measure. So the outstanding features of that plot are what the 1980s far infrared already saw, two very prominent bands that are our single Magnon bands, and this one that splits twice as fast, which is a single ion bond state. But what we saw in this data is also many other lines that seem to come from high energy that have even a larger slope than the single ion bond state. And so what Annuel Legros did is extract the position of all of these peaks as a function of field. So this is your 1 Magnon excitation that we've already talked about. We have the 2 Magnon excitation here that is a single ion bond state. So, but it's 2 delta Z equal 2, so twice the G factor. And then if you fit this these lines here, you realize you have 4 times the G factor and 6 times the G factor. And so in fact, these excitations are 4 Magnon. So a 4 Magnon excitations is a bond state, an exchange bond state of 2 single ion bond states. And then you can even see the 6 Magnon bond state where you flip the spin twice on 3 sides next to each other. And because there is a ferromagnetic interaction, this binds a little bit and creates a 6 Magnon bond state. Again, why do you see these excitations? Because they are all mixed by spin-orbit coupling. They all have a little bit of 1 Magnon character, and therefore they have a cross-section to optics and neutron scattering. What is the message here is that we have a system which has a dominant single ion anisotropy and a little bit of exchange around it. So in some sense, you can imagine it's almost a flat band system. It has a small bandwidth. So because there is attractive interaction around the small bandwidths, well, you're going to stabilize a lot of different bond states. So these higher order bond states come from attractive interactions. There's little kinetic energy, a lot of potential energy, so all these bond states can form. And the magic is that we can see them because of essentially SZ is not a good quantum number. There's a little bit of spin-orbit coupling that tilts this, and all of this is spectroscopically active, so to speak. So the theorists have developed a way to understand this, and in fact, this is the theory here, where you can actually understand this data, in particular the 4 Magnon bond state, by working in SU3 and keeping 2 flavors of particles. Now you're going to imagine the single Magnon and single ion bond state are 2 different quasi-particles, and by keeping the 2 particle sector, you can do exact diagonalization, and you can essentially understand this this data. And in particular here, you see this 4 Magnon state that is coming down and changing the picture quite drastically. If you were to do that without using SU3 without using that technique, you would need to go to infinite order in perturbation theory. But they found, Battista and Hauseng found a smart way to do that. So trying to accelerate here a little bit to finish on time, one important aspect here from potentially, let's say, the many-body physics point of view is that you have a system that has, at least 4 flavors of independent quasi-particles with different quantum numbers. And there is a region of energy and field where all these particles seems to be, overlapping. So that's an interesting playground for many-body physics. How do these particles actually interact with each other? We know that they all have a little bit of single Magnon because we can see them, but we can also ask, how do they interact as quasi-particles? And so one of the ways to do this is to extend these measurements that we have done again with optics at Q equals 0 with neutron scattering, where now we apply magnetic field and we can look at things at finite momentum. And so this is done on this outstanding machine at Oak Ridge National Lab called ISPEC, where we can work with very high field magnets, and it has a geometry that makes the background from these magnets essentially absent, so we can do very nice spectroscopy. And so this is what you see here. This is our initial data that I showed, 0 Tesla, and now we apply field 1 Tesla, 2 Tesla, and these arrows are here to guide you through what are these excitations. And you see the beautiful splitting of the excitations, single Magnon splits, the single ion bond state splits, and then Singh starts to cross. And when we continue to apply magnetic field, interesting thing starts to happen, in particular here at 4 Tesla. So if you look at the data at 4 Tesla here, what you see is that you have the single ion bond state that is a well-defined branch. Okay, so you see the single ion bond state here is a well-defined quasi-particle. It has a sharp dispersion curve everywhere, same here. And suddenly here, this sharp dispersion curve becomes broadened and essentially disappears in a continuum here. Okay, and what you see is that the linear flavor wave theory, so to speak, seems to not predict that result. And the explanation here is that there is a decay of the particles into each other. So we also, so that's the assumption, or that's the, if you see this, you say, oh, my quasi-particle is decaying. And when you do a cut in energy, so imagine we cut in energy, we see that the width of the particle is indeed much larger than the resolution of the experiment. And the way to understand this is also to consider the effect of anisotropic exchange. But no, it's another term in your Hamiltonian. The J plus minus term actually allows certain diagrams in the theory. So here what we are doing, or rather what Christian Battista's group is doing, is a one loop correction to SU3 spin wave theory. You're doing one, like in traditional spin wave theory, we do 1/s expansion. And so as we go, we include diagrams that model Magnon interactions. So we can do the same here, where we do a one loop correction to our flavor wave theory, so to speak. And this term here enables the following diagrams. And in particular here, you see, this one is relevant for what I'm talking about. You see a single ion bond state. This double line is a single ion bond state, and it can decay into two single Magnon. And this is kind of what is going on here. You also have a process where a single ion bond state, a single Magnon, traditional Magnon, emits a single ion bond state and continues its way. So these processes are activated by this term in the Hamiltonian. And because we have the magnetic field, we can tune the energies of these excitations, and we can really make this, we can fulfill the kinematic conditions for decay. And so these decay processes actually happen in the system. Okay, so there's even more interesting stuff that we can do. So in this one loop expansion, we only consider single Magnon and double Magnon, the single ion bond state, but we don't have 4 Magnon bond states because they are exchange bond states. And it turns out that these 4 Magnons actually suppress decay in certain cases. So here at 3 Tesla, the theorists were telling us you should see strong decay, and it turns out in the experiment we don't, and that's because coming in the party is this 4 Magnon bond state here. That 4 Magnon bond state essentially prevents the bond state to decay and make hybridizes with it and forces it down. And so there's a lot of many body physics of these bond states that we can see here in the material. So let me try to wrap up and give maybe broaden the picture a little bit. So it started as we want to solve the magnetic structure of this material in high field, to essentially discovering that there is a little world of interacting quasi-particles in that system. We have 1, 2, 4, and 6 Magnon excitations. I will point out that there are other materials also with magnetic ordering and large spin, such as the sodium manganese oxide by Rebecca Daly. They also observe 3 Magnon excitations. So there is exotic physics even in systems with magnetic ordering and large spins. What we observed here is the decay of this quadrupolar and single Magnon excitations into different types of 2 Magnon bond states. And we also observe this avoided Magnon decay by recombination of decay products, where you decay into 2 single ion bond states, but they can combine into a bond state themselves. And so there is essentially a lot of interaction physics here. So maybe a little bit more out there, I would say that this has analogies to neutrino mixing, although this is of course not my specialty. In the standard model of particle physics, we believe there is electron, mu, and tau neutrino, but in fact they are mixed together into 1, 2, and 3 neutrino. So the flavors of this neutrino is not perfect in the standard model. And here it's a little bit the same. We have 1 Magnon, 2 Magnon, 4 Magnon. They are not exactly the eigenstate of the Hamiltonian. They are all mixed a little bit. And that's why we can see them spectroscopy. So that's one spectroscopically. So that's one nice aspect of the system. And another thing closer to condensed matter physics is that what we see here is a lot of flat band physics, so to speak. So we have essentially flat bands that are these bond states, and they hybridize, and they are very narrow. They have small bandwidths, and if you treat the problem without hybridization, you have your 4 Magnon bond state, your single Magnon, and your single ion bond state here, and they overlap. And so now there's a hybridization, and so you're creating, there's flat band physics, and you're creating this bands with heavy, light, or super heavy nature in the system. So there's all the consequences of this, of having this multiple flavors of magnons. So the group of Daniel Loss proposes that if you look at the topology, so naming the excitations at the boundary of the system, there will be exotic effects. I just want to say that we are on our way to, here we just looked at low field physics, but we're on our way actually to understand the high field physics as well. And so there's a lot of problems that this material, we use it as the way to push the frontier of neutron scattering, push the frontier of how we analyze the data. So here's an example where we looked at the excitations at 14 Tesla on this iSpec machine. We're also learning how to describe the system at finite field and finite temperature. So this relies on what is called Landau-Lifshitz dynamics. Kristen Batista's group is working on this. And we actually have a computer code we call Sunny that allows to do these calculations even experimentalists can do it, so to speak. And so if you're interested in this, the beginning of this code is on GitHub. And so with this, I'd like to thank you all for your attention and take your questions. And again, it's a great pleasure to talk to you today.
Thank you, Martin.
Thanks for a nice talk. I have two questions. One is about your analogy to neutrino mixing.
So the analogy I should not have done. Yeah.
No. There's a famous neutrino oscillation. Whenever two modes hybridize, if you put it in the initial state, it can do Rabi oscillation. So I wonder if such a thing could be done in your system. For example, in some ferromagnetic resonance experiment, you apply some external magnetic field and then look for some oscillations. It's a very wild suggestion.
No. This is fantastic. So I will say this. I thought about the neutrino oscillation aspect, and the way I was saying this was that when you move in momentum space, because you're hybridizing differently, essentially as you move in momentum space, you have your neutrino oscillations because these different Qs have a different hybridization. But what you're suggesting is in the time domain. In fact, we are on our way to develop in my lab a pulsed electron spin resonance setup. So where so essentially we would use the techniques of pulsed ESR to study this and studying that.
So my second observation.
So I think that's a great idea.
I have a short observation. When I looked at your complex phase diagram, I was reminded of cerium antimonide phase diagram. Then I noted that Louis Renaud, in his French text, which I don't understand, I noted cerium antimonide. So what does he say? Is he showing an analogy?
Okay.
Because cerium antimonide has a devil staircase and complex phase diagram.
Yeah. Okay, so that's fantastic. So he's making a point about the particular technique that we need to use to understand this phase diagram. So the problem is the following. So all these phases have a propagation vector that is three-dimensional. So say 1/4, 0, 1/4. So you need to apply a magnetic field, and at the same time, you need to detect magnetic reflections that are out of plane. So you need to have the capability, usually our magnets restrict us to a certain scattering plane. But at the time at CEA in Grenoble, at the neutron source before the ILL, they had a diffractometer that is called a lifting arm diffractometer. So you can go and look at reflections out of plane while applying magnetic field. And that's what you need to solve that phase diagram. And that's also what you need to solve the phase diagram of cerium antimony. But I had not made the connection that it's not only a technical similarity. What you seem to be saying is that it's also a physical similarity. So the devil's staircase here is actually not completely apparent in that diagram. We actually did specific heat measurement at very low temperatures, 300 millikelvin or 200 millikelvin. And when we go across here, we see that it's not 1, 2, or 3 phases. It's many different phases. So it seems to resemble cerium antimony per what you're saying.
I'm very happy. Okay.
And my understanding of this is that, and the direction in which we are going with this is that, you know, there is also dipole-dipole interactions in that system. So you have essentially Ising system with many different, you know, magnetic structures that may have, you know, equivalent energies. And now the dipole interaction that is very small, but at low temperature will play a role, right? The dipole interaction will split them in many different pockets. So we are on our way to understand this. It's actually very difficult. I had not made the connection with cerium antimony, so I'm very glad you're telling me. It's more than technical, it's actually physics. The physics might be similar. So I was not aware of that. Thank you.
Maybe we will correspond, yeah.
Yeah, that would be great. So I'm ignorant about this and I should know.
Is there any more questions? Anything from the online participants? Does not look like the case. So let's thank Martin again.
Thanks, everyone.